Recording started.
All right. Hi, ch20 students. Welcome to our first session here. And we're just going to kick this off. Actually, our first slide was just a little picture of the periodic table of meats, which was, I thought, sort of interesting. So I thought I would just show that to you guys. And now we'll get more into the meat of the subject, no pun intended. So talking about the periodic table then, the periodic table is just that. It's periodic. And in other words, there's regular patterns to it. And so elements found in the same group have similar properties to one another. And so just a reminder of what we're talking about when we're talking about the same group, that's elements in the same column. And when we're talking about elements in the same row, those are known as periods. So I'll just kind of pop up a picture of the periodic table here for you guys. I think that might be a little big, so I'll just make it a little smaller. Okay, so again, we're talking about these columns being the groups and these rows being the periods. And now later on we're going to talk about something else. Well, hi Ashley, did you get disconnected again? Ah, that's too bad. Have you been in other people's classes as well? I'm just wondering if it's just mine, or is it your internet connection, do you think? Ah, okay. Tell them to stop watching those videos. Anyways, okay. Well, hopefully it works okay this time. Just a reminder then, guys. So these are groups and these are periods here, and we're going to refer back to the table later on. So going on to page 2, just going to make that a little bigger so you can see it. Okay, so I want to ask you guys which element is found in column 13 in period 3. So we need to know how to do questions like that. So column 13, period 3. Okay, so can somebody tell me which column, or rather which element that is? It's found in column 13, period 3. Okay, aluminum, good. Did you guys get aluminum as well? Sometimes this period here, because it's kind of in a, H is kind of in a class by its own, we sometimes don't think to count it, but that is one of the periods as well. Okay, good stuff. So moving along, remember that atoms are made up of protons, neutrons, and electrons, right? But remember that it's only the electrons that take place in chemical reactions. And I got a bit of a correction on what I just said. It's actually not the electrons, it's the valence electrons. So if you guys remember, the valence electrons are just the outer electrons. Remember, electrons are in different shells. And so it's just the outer electrons that actually take place in chemical reactions. So just thinking, for example, of chlorine, it has the atomic number 17. So if you look on the periodic table, you'd see that number 17 there. And that number means that chlorine has 17 protons and 17 electrons. So the atomic number is kind of the number that we use to identify all the different atoms of or elements of the periodic table. Okay, so because it's got 17 electrons, we know 2 go in the first shell or energy level, 8 go in the next one, so that's a full energy level, and then 7 are in the outer energy level, and so those ones are the valence electrons that take part in chemical reactions. Okay, so here's what it looks like. Here's what chlorine looks like. Here are the different energy levels, and as we can see, there are 7 electrons, 7 valence electrons in the final level. So when you think about the fact that elements want to, or rather atoms want to have a stable outer shell, which is made up of 8 electrons, it really makes sense that chlorine would want to gain 1 more electron, right? It's not going to want to get rid of all 7 of these electrons. So with some atoms, it's a little less clear than that. You're not sure if they want to gain or they want to give. But with chlorine, you know that it just wants to gain 1. And as soon as it does, it's going to be happy. It's going to have an outer shell of 8. Okay? So also remember the fact that we talked about already the fact that the valence electrons are the ones that give the chemical properties. Okay, so if you have a number of atoms and they all have the same number of valence electrons, or they're in the same column, they're going to have similar chemical properties. Okay, and I want to show you guys something as well. In the periodic table, even though we have all these different columns, we usually kind of ignore the transition elements as far as finding the valence electrons, and that's because if you look in your periodic table in your textbook, it's going to have more than one charge for these guys. Like it might say +2 and +4 for manganese. Okay, so what we do to find the valence electrons is we label, sorry, I just got to get my right thing here to label this. We label these guys here, these columns, and I'm just going to make that a little bigger so you can see it better. Okay, so we label the first two, and then we skip all of the orange ones, which are the transition metals, and then we go on and label the next ones. So the column numbers that you see here tell you the number of valence electrons, and again, those are the electrons that are available to participate in chemical reactions. Okay, so be aware of how we label those, skipping the transition elements. Okay, so let's see what page we're on. I think it was this one, and I think we're done this one. Okay, so here's a question then for you guys. What determines whether two atoms will have similar chemical properties? How would you answer that? Here's another way of saying it. If they have similar chemical properties, they're both going to have the same number of what? Okay, it's electrons, and it's just, in particular, it's the valence electrons. Okay, good stuff. All right, so when we talk about the reactivity of elements, what does that word reactivity mean? Well, remember, the more reactive an element is, that's the more it wants to react with other elements either to gain or to lose electrons. That's what we mean by the word reactivity. Now, if you think about where the most reactive elements are found on the periodic table, they're either found in columns 1 and 2, so the metals, or column 17. That's the second last column, and those are the halogens. So if you look at the picture here, it's got a picture of sodium, and believe it or not, sodium actually burns underwater. In fact, years ago when they had this oil spill underwater, I was kind of thinking to myself that maybe what they should do is get some sodium and burn that underwater. And I don't know, though, what would have happened if they would have burned the oil, and if that would have produced a larger problem. Just an idea, though, anyways. So sodium, believe it or not, it can burn underwater. Really bizarre. So the halogens, which are in column 17, those are like bromine, chlorine. Remember, guys, that those appear as what are called diatomic gases. So in nature, they appear as two atoms joined together. So Br2, Cl2. Okay. Okay, so question here for you guys. And then question 3. In which columns are the most reactive elements found? Okay, first column. Any others? Also 17 and 2. Yep, those are the most reactive. Good stuff. Okay. You guys remember in Science 10 we talked about the difference between physical properties and chemical properties? So basically physical properties are properties about some sort of element that we can see, taste, smell, that sort of thing. Okay, so if we're talking about, say, the color, the hardness. Also, if something conducts electricity, that's actually a physical property. Okay, if you're talking about chemical properties, they always have to do with how that element reacts with other substances, so like water and oxygen, often you're talking about. Okay, now, if you're talking about something like sodium chloride or salt, remember it breaks into ions. So when you take sodium chloride, it breaks into Na plus and Cl minus. And so those two ions are what give sodium chloride the ability to conduct electricity in water. And I don't know if you guys remember, those of you who had me for Science 9, I talked about the fact that when you're doing like a lie detector test, it's because of your sweat produces sodium chloride, produces salt. And so that's what actually allows the lie detector test to do its job, because it's conducting electricity, the amount of sweat that you have. Anyways, so let's just review again what the main groups are in the periodic table. So group 1 is the alkali metals. Group 2 is the alkaline earth metals. Name's kind of similar, right? Group 17 is the halogen gases, as we said. And group 18, those are really, really kind of bizarre elements that don't really want to do a whole lot. They don't want to react. They don't really want to play with the other elements. So because of that, we say they're noble gases or inert gases. Okay, so it's important to know the names of these guys. Okay, so a couple questions for you guys. First question, number 4 here. What enables ionic solutions to conduct electricity? What do they break down into in the water? That's right, they produce ions which have chemical charges. Okay, question number 5. Name the element groups found in 1, 2, 17, and 18. If you can't remember them now, that's okay. But do you guys remember any of those? Okay, alkali metals, first one. Second are alkaline earth metals. 17 halogens, and 18 are noble gases. Good stuff, right on. Okay, what she said, yeah, exactly, eh? All right, so guys, we're going to talk here just a little bit about why it is that elements react. So if we think about sodium, if we look on the periodic table, we see it's in column 1, so it has one outer electron, one valence electron, right? So it looks like this. So if you think about it, the easiest thing for sodium to do is to get rid of this electron, right? Now what happens if it gets rid of an electron? Because right now it has one electron, one proton. Well, it doesn't necessarily have one. I shouldn't say that. It has one outer. We'd have to look on the table to find out how many it has. Let's just pretend it has 10 of each, 10 electrons, 10 protons. Now, if it gets rid of this one electron, it's going to have one less electron, so it's going to have more protons than electrons, right? So you can see why sodium will then have a +1 charge, right? Now, if you look at oxygen, it's in group number 6. So because it's in group 6, we draw 6 outer electrons. Now remember, when we're drawing the electrons for chemical reactions, first we draw 4. So we draw them in kind of north, south, east, west direction. And then once we get 5, then we start pairing them up. Okay? So here's what oxygen looks like. And you can see that the easiest thing for oxygen to do is to gain 2 electrons, right? To gain one that's going to pair with this one and one that's going to pair with this one. Now if it gains 2 more electrons, it's going to have a -2 charge, right? Because electrons are negative, so you've got 2 more electrons, 2 more negatives than positives. So you can see you're going to have a -2 charge. Okay? So that's just kind of a bit of a review about what happens when elements react with one another. Now the important thing to know is that when sodium loses that electron to get a +1 charge, that ion, that Na+1 ion, is the most stable form of sodium. And likewise, O-2 is the most stable form of oxygen. Okay? So atoms are not the most stable forms. It's their ions that are the most stable forms, right? Because they have these outer shells that have 8 electrons in them. And so I just put here, I said, just like with birds, you can see this guy, stability is a good thing with the bird, and same thing with electrons. All right. So now we're talking about the reactivity of metals. So just remember, guys, when you go down the periodic table, then metals become more reactive. Okay, and we talked just really briefly, we just kind of looked on the periodic table about transition metals. So remember that those are in columns 3 to 12, and remember that these are metal atoms that have 2 different possible charges with them. Okay, so when you look in the table, you're going to see numbers like +2 and +4. Okay, so here's a picture of an atom, right? Kind of cool. The electrons are much, much smaller than the protons and neutrons. They're tiny little guys and they just zip around all over the place. Okay? So most of the weight of the atom comes from the proton and the neutron. Now, when we talk about the weight of the nucleus of the atom, the proton and the neutron combined together, that's the atomic mass. Okay? The atomic number is the number of protons, or the number of neutrons, or sorry, I should say number of electrons. So protons and electrons are the same for an atom because it has no charge, right? Okay, so remember, one of the numbers on the periodic table is the atomic mass. It stands for this. And the other number is the atomic number, which stands for protons and electrons. Okay, so let's say we have a little problem here. Well, first of all, before just leading up to that, sometimes you see kind of a symbol that like this here, and what that really stands for is for sodium. It tells us that the atomic mass is 23 and the atomic number is 11. And so now we know what those numbers stand for. Now what if you were given just a little symbol like this, and the question says, you know, how many neutrons are there? Well, the way we'd find the number of neutrons is we would look at the fact that the 23, the upper number, stands for neutrons plus protons, sorry. Lower number stands for protons. So if we subtract atomic mass minus atomic number, you can see that that will give us the number of neutrons. So if we subtract 23 minus 11, that'll give us 12. Okay, so that's how you can find that. All right, so another question for you guys, number 6. State the trend in the periodic table as far as the reactivity of elements. Okay, so we're talking about kind of what direction you go in the periodic table as far as when elements are more reactive. What would you say? Okay, up and right. Well, actually, it's within any column. The further down you go, the more reactive they are. And the ones on the left are actually more reactive as far as the metals. But then maybe you're thinking, okay, but maybe you're thinking like on the right-hand side you have the halogens, which are in group 17, and they're also fairly reactive. Okay, that's cool. All right, so question number 7. Find the number of neutrons for an atom that has an atomic mass of 25 and an atomic number of 12. Good. So just 25 minus 12 is 13. Good stuff. Okay. So you guys remember hearing about isotopes? Sometimes you hear about you know, chemists studying isotopes, especially like really high-level chemists. They deal with isotopes. So what are isotopes again? They're the same atom, but that same atom can have different numbers of neutrons. Okay, so if you're talking about neon, for example, all neon atoms have 10 protons. And that again, remember the number of protons or electrons is the atomic number which defines an atom. But some neon atoms have 10 neutrons and others have 12. So for some of those that have 10 neutrons, we would draw the symbol like this, and the other one would be this. This one has 12 neutrons. Okay, so now remember that because they have the same number of protons or electrons, their chemical properties are the same. So these two different types of isotopes for neon, their chemical properties are going to be the same because they have the same number of electrons. And again, it's only the electrons that determine the chemical properties of an atom. Hey there, Ruth. How's it going? I just noticed you joined. Good to have you. How's things in Slave Lake? How are things healing up in that town? I know it's been a bit of a process there, right? Hey, that's good. Right on. So are a lot of people whose houses, you know, whether if their houses have been damaged, possibly, are they starting to rebuild at this point? Yeah, I bet it's kind of a mixed bag, eh? I know when we drove through Slave Lake, I was kind of expecting to see more damage with the restaurants and stuff, but it was kind of more in the residential area. Is that right? Okay. Yeah. Well, I'm glad things are getting better, because that was sure quite a rough time for everybody, eh? Yeah. Hey, so Ruth, what we're doing here is we just finished talking about isotopes, and we said that isotopes are basically two different forms of the same atom. They have the same number of protons and electrons, but they have different number of neutrons. So they have the same chemical properties because they have the same number of electrons. Okay. So if you were to answer question 8 here, what is similar and what is different between two isotopes of any atom? Okay, the mass is going to be different, right? Because they have a different number of neutrons. Okay, protons and electrons are similar, neutrons are different. Good stuff. All right. So, we're talking here about ionic and molecular compounds. Now, hopefully you guys remember the differences in how we name these two kind of compounds. Because I know sometimes this gets a little bit tricky, but once you catch on to it, it's not too bad. So these are some examples of molecular compounds. These are ionic. Ionic compounds tend to be crystals. They form kind of really rigid, repetitive sort of structures. And so those are kind of examples of each one. So calcium chloride would be an example of an ionic compound. Remember that ionic compounds are formed by a metal joined to a nonmetal. So metal, first 2 rows of the periodic table generally, nonmetal somewhere in the right-hand side of the table. Remember with ionic compounds, the subscript 2 does not affect the naming of the compound. So this is not calcium dichloride, it's just calcium chloride. On the other hand, if you're talking about a molecular compound like carbon dioxide, first of all, it's formed by a nonmetal plus another nonmetal. In this case, the subscript 2 does affect the naming, so it's carbon dioxide. And remember again, it's dioxide, it's not dicarbon oxide, right? Okay, now keep in mind something else. When you're talking about the differences with ionic and molecular compounds and how they form, electrons are actually transferred from one atom to another to form an ionic compound, but with molecular compounds, electrons are just shared between atoms, and those are called covalent bonds with molecular compounds instead of ionic bonds. Okay, so question 9, what's different in the naming system of ionic and molecular compounds? Okay, so subscripts don't affect the name with ionic compounds. They do with molecular. Good stuff. And so question number 10, what's different in the way the bonds form in these two compounds? Okay, so you just have a sharing of electrons with molecular compounds, but you have ionic compounds actually, the electrons are actually transferred. And as Adam pointed out, the bonds are actually stronger in ionic compounds as well. And we'll see later on how that affects the relative boiling temperature of ionic and molecular compounds, the fact that ionic compounds have stronger bonds. I just wanted to ask you guys if possibly you guys want to get a drink or something like that. Just take a little break and get a drink or something. Anyone want to do that? No problems, I know what you mean. Okay, Mitchell, you got to go? That's okay. Thanks for coming. Oh, you're good to go. Sorry, I thought you said I got to go. Sometimes you just read the stuff popping up and hey, no problem. No, you said it right. I just read it wrong. Okay, you okay, Adam? All right, good stuff. So going on to the next page, When we talk about ionic compounds, there's some different characteristics of them. For instance, they're very neutral, and sorry, I meant to say they're very brittle. That doesn't really make sense. Very neutral. But the fact that they're neutral is because of the fact that the two charges cancel out. So you have Na plus Cl minus. They kind of cancel out. They're very brittle. They conduct electricity when dissolved in solution, and they're made of a metal plus a nonmetal. Okay, now we're going to go into a concept known as electronegativity. So what is that? Well, it's a measure of how strong an atom is attracted to electrons. How badly does it want them, right? So now one important thing to know is that ionic bonds are formed between two atoms. One has a high electronegativity and the other has a low one, okay? And that has to do with the fact that they're found on different sides of the periodic table. So for instance, when you have NaCl, Na is found on the left side with the metals, Cl is found on the right side. The ones on the right side have a higher electronegativity, ones on the left lower. And we'll see how electronegativity, the importance of it later on. Okay, so when we're talking about the traits of ionic compounds, maybe I won't ask you guys to list all these, but just to let you know, these are important to know. Metals are on the left side, columns 1 and 2. We also have the transition metals in columns 3 to, I forget what it is, 12 maybe. But they're columns 1 and 2 mainly. Okay. All right. So know the different characteristics of ionic compounds. All right. So this is actually not a periodic table of elements. This is actually called the electronegativity table. So I hope you guys have had a chance to look at those in the questions. But here's a question to figure out: which pair of elements would form a stronger ionic bond? Would it be O and H, or would it be S and Li? Well, the way we figure out which forms a stronger bond is we look at the electronegativity using this table. Okay, so when you guys have the first test, you will have this table available. You can use it, the one that's in the textbook. So the way you find which is a stronger bond, you find the En value, and then you subtract the two and find what the difference is. So you can see the difference is 1.4, and here the difference is 1.5. And so because this is a larger difference, this is going to be a stronger ionic bond. Okay, so the larger the difference in electronegativity between two elements, the stronger the bond. So, okay, here's a question for you guys. Which atom would have the highest electronegativity? Would it be potassium, cadmium, or tin? Remember, tin's kind of funny. It has Sb as a, you think it should start with a T, but it's Sb. So looking on the table, do you think it is K, Cd, or Sb? Okay, Mitchell says Sb. And I believe that was the right answer. Is it, sorry guys, I can't seem to see all three of them right now. Is anybody else getting Sb? We got 1.7. I think it's a little bit small, eh? Okay. So basically you just have to see which has the largest number. And like Ruth, a few people said it, Sb. Okay, good stuff. Now, again, I mentioned before that the highest electronegativity is on the right side, lower is on the left. So switching gears here, I'm sure by now you guys know it's important to know these different prefixes for naming molecular compounds. So be able to memorize the prefixes from 1 to 7. Okay, so know what each one of these stands for. Question 14 then, how does the electronegativity relate to the strength of bonds in a molecule? Okay, remember it has to do with the difference in those En values. And how does the difference in En values relate to the strength of a bond? Yeah, the bigger the difference, the stronger the bond. Good stuff. All right. Okay, so we're going to talk now about how Roman numerals are involved in naming transition metals. So you might see a compound like this, manganese 4 oxide. And sometimes when people see that, it kind of throws them off because they think that the 4 that's in manganese 4 oxide, the Roman numeral 4, they think that that has to do with this or this. So if this was like a multiple choice test, some people might pick this or some people might pick this. But in actuality, that 4 doesn't have anything to do with anything that you see in the formula. So here's why. Remember we said that transition metals can have 2 different forms, like Mn plus 2 or Mn plus 4? That's right, you have to cross multiply, and that's where it's going to come into play. So where the manganese 4 comes into play is that it's this form on the periodic table, the Mn plus 4. So again, you're going to see 2 different numbers there. It's this form that's going to form manganese 4 oxide. And here's how it works. You're going to have manganese plus 4, so you know that's the one you're going to use. You know that oxygen is minus 2 because you see a little minus 2 in the periodic table. And then you're going to cross, like Mitchell says, you kind of cross multiply. So you bring this 2 from oxygen down here, bring the 4 to follow after the O. And so now you have this here, but you always need to name a compound in the simplest form, right? So because of that, you divide 2 into both 2 and 4, and so you get Mn1O2, and you just ignore the 1, so it becomes MnO2. So you can see why I said that you can't look at this formula and tell that it's manganese 4 oxide. The manganese 4 just tells you the ions that you used to form the compound. Okay? So this little section here is just kind of reminding you that we put compounds into simplest terms, so we just divide the largest number that will go into both numbers, and so that's what we did here. Okay, so question 15 says, what does the Roman numeral in the name of a compound that has a transition metal in it tell you? It's the charge number. That's right, it's the charge number on the transition metal. Good stuff. All right, we're going to talk about these beasts called polyatomic ions. Okay, you probably remember from Science 10 you had to know some of these guys. What I would like you guys to know is the polyatomic ions other than the ones that have been crossed out on this chart. Okay, so be able to recognize that this is ammonium. Basically be able to memorize both the ion and the name for all the ones except for the ones that are crossed out. For the other ones, you may need to use those to answer some questions, but you wouldn't need to memorize them. Okay? So again, remember a polyatomic ion, the whole ion functions as if it's one element. So it's a group of elements together, but it functions like it's one ion. Okay, so what do you think? What would the name of sodium sulfate be based on what you see on the chart? Would it be NaS or would it be Na2SO4? You can just say first or second. Yeah, it's going to be the second one because this is sulfate, right? You see on the chart here, this is sulfate, SO4 minus 2. So you can see those are going to cross out and produce this compound here. Okay? All right. So, guys, be able to identify especially these ions here, ammonium, nitrate, sulfate, phosphate, and carbonate. Basically, if you memorize that chart, you're going to know those ones. Also important to remember, if you know what's called the ate form of an ion, okay, so the form that ends in ATE, then you can find the ite form. Okay, basically the ite form will always have one less oxygen. So if the sulfate form has 4 oxygens, the sulfite form is going to have 3 oxygens. Okay, so that's how this works with the ate and the ite. Okay, the next question here is talking about predicting the ratio of ions in a compound. So let's say you had a question like this. What would the ratio of metal to non-metal ions be when aluminum reacts with oxygen? So of course we know that aluminum is a metal. We know from the periodic table its charge is +3. Oxygen, a non-metal, has a charge of -2. So first of all, we just take the ions and we cross multiply like we did before. and we get this here, Al2O3. So we can see that we have 2 metal ions, 3 nonmetal ions. So we would answer this question by saying that the ratio of metal to nonmetal ions is 2 to 3. Okay? Good stuff. All right, so next one. We're talking about Lewis structures. Are you guys pretty okay with Lewis structures? Okay, that's good. Right on. Well, if you come across any that you need some help with, we will go into those, and we'll go into this question right here. So this question says, what would the Lewis structure look like for CH4? So the way we would find that is we look on the periodic table, and we would find that H has 1 valence electron, C has 4, and so because of that, each one of these H electrons is going to pair with the unpaired C electron, and so we get the structure that looks like this. So that's going to be our Lewis structure. All right, question 19. It says, which of the following is believed to contain 3 lone pairs of electrons, A, B, C, or D? Okay, so how do we find that? Well, first of all, we need to focus in on what are lone pairs of electrons. What are we talking about there? This is going to have to do with lone pairs and bonding pairs. Okay, so we know S is in column 6. That means it has 6 outer electrons. Sorry, Mitchell, you're saying that likes to... sorry, what is that? Just explain a little bit more what you meant by that. Yeah, that's right. That's right. They're the same 2 electrons. Good stuff. Okay, so sulfur is in column 6, has 6 outer electrons. Phosphorus has 5, column 5. And again, based on the column number, we just put the number of electrons. Again, first of all, we put 4 in the north, south, east, west direction. And if we have 5, we start pairing up. So remember, the 3 electrons that look kind of like this, you can use a colon if you want to kind of type it out. Oh. Hey, Ashley, you got kicked out again? Are those sisters still using up the bandwidth there? The rascals? Just kidding. Okay. So this question was saying, which are the lone pair electrons? Which of the atoms has 3 lone pairs? And it turns out it's going to be chlorine, right? Because each one of these is a lone pair, like Mitchell was saying earlier, right? So chlorine is going to be the one that has 3 lone pairs. These electrons here would be taking part in chemical reactions with other atoms. So those would be bonding pair electrons, right? Okay, so remember those lone pair electrons and bonding pair electrons are important when we have to try to figure out the shape of an atom. Remember, we have a chart in the textbook, and based on the number of lone pair and bonding pair, I think it's on page 55, that helps us to figure out what the shape will be. Okay, so this question says, what's the correct Lewis structure for AsCl3? So first of all, we find out As has 7 valence electrons. Cl has 7. Sorry, I meant to say As has 5. Cl has 7. So I said we can see that As has 3 unpaired electrons, and each one of those unpaired electrons is going to bond with 1 Cl. So I'm not drawing all the electrons in, because there's all kind of electrons around here, but I'm just drawing the 2 unpaired electrons here. So again, you might be given some sort of question like this type, and then again, using the chart on page 55, you can figure out what the shape will be based on the number of lone pairs and bonding pairs. Okay, so again, you'll be given, on the test, you'll be able to use the chart that's on page 55. So Ruth is saying it's trigonal planar, and it's actually trigonal pyramidal. And sorry, I don't have the chart in front of me right now. But what this one boils down to is it's known as AX3E. So remember, the A stands for the inner atom. The X3 is the outer atoms. So we have 3 of them. And we have 1 lone pair electron, so that's why it's AX3E, and that's why it would be trigonal pyramidal. Does that make sense based on page 55? For those of you that have the textbook open there? Okay, so again, this is the type of thing we come up with to help us find what the shape is. Okay, good stuff. So that's kind of the process in finding the shape from the chart. And here's what it actually looks like, trigonal pyramidal, just to see what it looks like. This is NF3, so it's a different molecule than the one we were looking at. Okay, so shifting gears again, we're going to look at differences in the types of forces that exist within molecules and between molecules. So think about the word internet, right? What is the internet really? It's kind of a connection between computers that are all over the world, right? So intermolecular forces are between molecules, whereas intramolecular are forces within the same molecule. And cyber high is kind of an intranet, right? You can think of it that way. Now the differences between the different kind of forces we're going to talk about is how strong they are, or at least that's one difference. Remember, dipole-dipole forces are weak attractions between the poles of molecules. Okay, so what happens is you have an unequal sharing of electrons. So the electrons share more of their time, spend more of their time here than there. So because of that, this is more negative. So this side of the molecule becomes more negative. This side becomes slightly more positive. Again, they're weak forces, right? But what happens is the negative from Cl is going to be attracted to the positive from another HCl molecule. Okay, so there's a picture of that here. So you can see a bunch of the molecules together. You can see this one's slightly positive, and that's attracted to this side here that's slightly negative. Again, it's a weak attraction when we're talking about a dipole-dipole force. When we talk about a hydrogen bond force, hydrogen bonding, when we talk about hydrogen bonding, that's what gives hydrogen, or rather what gives water its unique properties. You think about the fact that with water, most of the time when you melt a substance, it becomes, it takes up less space. Whereas with water, it takes up more space. So the ice form actually takes up, the solid form takes up more space. But it's kind of the reverse of most substances, right? And that's because of the fact that it has hydrogen bonding. So hydrogen bonding is actually a dipole-dipole force, but it's a very strong example of it. Okay, so it only occurs with hydrogen and some particular elements. Those elements are elements that are very electronegativity, so they're on the right side of the table. So oxygen, for instance, and that's why water that's in oxygen, and so that's why oxygen that's in water allows for hydrogen bonding. So what happens that causes this to happen is that the element, so this is hydrogen fluorine, actually, hydrogen fluoride, I should say. What happens is the atom that's very electronegative, the fluorine, it grabs all the electrons, or it grabs the electrons to a very large degree, leaving very few electrons near the hydrogen. So we say that hydrogen is unshielded by its electron, okay? Because most of the electron activity is going near the fluorine. Okay, so remember, the larger the difference between two atoms involved in a hydrogen bond, the stronger the hydrogen bond is going to be. All right, another type of intramolecular force, these are called London dispersion forces. Now, London dispersion forces are found in both molecular compounds and ionic compounds, so pretty well any kind of compound will have these. These are the weakest of forces. They're just kind of temporary forces that exist. Okay, so as electrons shift within molecules, electrons are temporarily attracted or repelled to electrons in other molecules. Okay, so now again, all of these forces, dipole-dipole, hydrogen bonds, and London dispersion forces, they're all intermolecular. They take place between one molecule and another. So those are intermolecular. Now on the other hand, interionic forces are the name given to forces that occur between ions. And I think maybe it was Adam, I'm not sure who had mentioned this earlier, mentioned that the forces that are needed to break ions are very, very strong. It's hard to break ions. Okay? So that's the reason why ionic compounds like salt have much higher boiling temperatures than molecular compounds. You have to break those strong ionic bonds. It takes a lot of heat energy to do that. Okay, so another question for you guys. What are two differences between interionic and intermolecular forces? The first one's kind of more, you could say maybe more obvious. It has to do with the name of those, interionic and intermolecular forces. That would be one difference. Okay, so from that I was, okay, sorry, I see that Ashley's typing something. That's right, one's ionic between ions, the other is between molecules. Can you think of another difference between these forces in terms of comparing them, strength of them? Ionic bonds are stronger, that's right. Okay, question 22. Can you order the intermolecular forces in terms of their strength? Which are the weakest ones? Okay, the weakest ones are the London forces, also known as dispersion. Do you know what the next weakest are? The next weakest are going to be the dipole-dipole, because remember we said at the beginning they are known as weak forces. And then the strongest are going to be the hydrogen bonds, which are a special type of dipole-dipole. Okay, so question here, which do you think would have a higher boiling temperature, H2S or H2O? And the way we find that is by looking at the strength of the ionic bond. And so we look at the difference in electronegativity, and we can see that there's a greater difference between H and O than between H and S, so there's going to be stronger hydrogen bonds. All right, question 24. So again, we see the EN value chart here. It says, which of the following chemicals is likely to exhibit evidence of London dispersion forces, dipole-dipole forces, and hydrogen bonding? Any idea? Okay, well, remember first of all we said that pretty much any ion or molecule has London dispersion forces, so we can kind of check that one off, right? As far as dipole-dipole forces, we would have to look at hydrogen and nitrogen and see whether the difference between the two was fairly large, because if it is, it'll produce a dipole, right? Now, which one of those four possibilities is the only one that can produce a hydrogen bond? A, that's right, because it's got an H and an N. And so just using that criteria right there, we know that it's going to be A. Okay? All right. So again, another question that's kind of similar. So question 25 says, explain why both ions and molecules have high hydrogen bond, or sorry, I'm getting ahead of myself. Why both ions and molecules with hydrogen bonds have high boiling points. So both ions and molecules that have hydrogen bonds, why do both of them have high boiling points? Okay, so Ashley says both of them have strong bonds, that's right. Okay, question 26. What type of intermolecular forces would exist in the molecule below? Okay, so it's going to be, first of all, we said London dispersion forces are going to be in all molecules. And then because there's a large difference between F and C, when we look at the electronegativity, it's going to have a dipole-dipole force. But with carbon and hydrogen, there's not a lot of difference, so that's not a dipole-dipole. But we are going to have dipole-dipole forces because of this here, this difference here. Are we going to have any hydrogen bonds, do you think? Well, I know where you're thinking that probably because we have hydrogen. But remember, in order for it to be a hydrogen bond, there has to be a large difference in the electronegativity between hydrogen and the other element. And because there's not a big difference between C and H, this actually wouldn't be a hydrogen bond. Okay? So we're only going to have the other two kind of forces. All right, guys, I think we're getting close because if I'm not mistaken, yeah, that's the second last page. So we're getting really close. Okay, so question 27 says, how would you describe the overall polarity of a diatomic molecule with a polar covalent bond? That's a bit of a mouthful, eh? You should come up to your parents tonight at supper and say, I learned about diatomic molecules with polar covalent bonds. And they'll just kind of look at you like, what? Anyways, so diatomic molecules, what does that mean, right? Well, diatomic just means there's two atoms in the molecule. Normally when you hear the term diatomic, normally that refers to things like, you remember in halogens when we're talking about column 17, we say that in nature they always exist as two molecules, or two atoms joined together as a molecule. So like Br2, Cl2, I2, column 17, right? Normally when you hear diatomic molecule, that's what you think of. But diatomic just means two molecules, right? Now the fact that it has a polar covalent bond means that it's polar, right? So one side must be slightly positive and one side slightly negative, right? So because of the fact that we only have two atoms, when it says here, how would you describe the overall polarity? Well, we know that because this is a polar bond, one side slightly negative, one side slightly positive, the overall polarity of the molecule must be, like overall it must be a polar molecule, right? It's not a non-polar one, it's a polar because one side is slightly positive, one side is slightly negative, right? So that one's kind of a little easier than the next one. The next question is talking about, here we have a molecule that has polar bonds, okay, so this side's slightly negative, this side's slightly positive. But even though it has polar bonds between these atoms, the overall molecule is not polar. And the reason is because overall it's balanced. These guys kind of, that's right, like Mitchell said, it's not going to be polar because the charges are going to cancel out because it's balanced or symmetrical. Okay? So if you have a symmetrical or balanced arrangement of the same atom, we have Cl surrounding it, the charges are going to cancel out. Oop, looks like Ashley left us again, unfortunately. So, hey Ashley, how's it going? I feel badly for you. So we were just talking about the fact that with this molecule here, although it has polar bonds, one side slightly negative, one side slightly positive, because the outside atoms are symmetrically arranged or balanced, overall this is not a polar molecule. On the other hand, this one is a polar molecule. And the reason is, even though the overall shape is the same as the one above it, one of the atoms is H. And so because of that, everything is not balanced, it's not symmetrical. So this molecule is polar, and this molecule above that has the exact same shape is nonpolar because the outside atoms kind of cancel each other out. So the last question for you guys is, explain why two molecules may contain polar bonds, but the overall molecule may not be polar. If it's symmetrical, that's right. And if it's symmetrical, then overall it will be nonpolar. Okay, right on, guys. So we went over a lot of stuff, didn't we, in this session here? And thanks a lot for coming to the session. And you guys participated really well. And I want to let you guys know as well, the stuff we went over in this session is going to be, a lot of the stuff is going to be on the test. Hey, no problems, guys. It's my pleasure. So I really tried to focus on stuff that would be on the test. So even though it may not have been exactly the same as the focus of the lessons, I tried to pick out the stuff that was going to be on the test. So as well, guys, if you have any questions from the lessons that you want to go over, I can always make you up another little video or something, like a recording or something. We can do it through email as well. I'll let you know as well when the first test is coming up. I can't remember exactly when it is, but I'll send an email about that. Are you using your microphone, Ashley? Hey, my sound is turned on. That could be it. Oh, okay. All right, just playing tricks on you. All right. Well, hey, guys. Hope you have an awesome rest of the week. I know there's not too much. To me, it seems like this week has just been kind of rushing by. And but hope you guys have a great week. And enjoy the summer weather. I know it's going to be getting a little cooler. Could be within the next few weeks we'll have snow. But hey, enjoy it while it lasts, eh? Don't say it or it'll happen, hey? All right, well, take care, guys, and I will talk to you later. Bye for now.